All right, today we're going to look at something called the Cauchy Euler equations. And this is another special case of linear higher order differential equations, but in this case they are not constant coefficient. So for the Cauchy Euler equations, if you look at the book, the way your book defines them is anything times a constant times t squared times the second derivative of the variable plus a constant b times t times the first derivative of your variable, then finally a constant times the variable itself is some function of g of t. And we are going to look at the special case where g of t is 0, so we're going to focus on the homogeneous case. So a, b, and c are constants, and we're assuming that our dependent variable is a function of time. Now, one thing that's going to be a little confusing is that you rarely see these equations in this form in practice. When they come up, they're often in the form of a times t y double prime plus b y prime plus c over ty is equal to some function. In this, when you do the derivations or you working with something, oftentimes, for example, something in polar coordinates, these kind of equations arise. And the way to deal with this is to, or the way we normally do things is we multiply everything by t, and if you multiply that through, you then get something in the form of what is in the book. And the reason why your author focuses on these, it's a little easier to justify what we're going to choose. And so now, just like what we did for constant coefficient equations, we're just going to make a guess. If the guess works, then we're going to go with it. So in this case, here's the thing, is we have a function, then we have t times the derivative, and then t squared times the second derivative. So we're looking for a function that when we take derivatives and multiply by t and then t squared, we get a like function. And the thing to recognize is that if I take t raised to a constant power, what happens to the t is I reduce it by one order. And here I'm multiplying by one order, and here I'm multiplying by two orders. So we're going to focus on this for our guess. Okay? So in this particular case, right, and just as a matter of completeness, each time we take a derivative, we're reducing the order down by one. So if this is the first derivative, and then r is a constant, we've reduced the order down by 2, and then we multiply by t squared, we're going to get a t raised to the r. Okay, so what this means then is that we're going to guess something that looks like c times t to the r. But notice this is a linear equation, so that means we can take the sum of solutions, and just as before, we're going to get two solutions, and we can just multiply those things by a constant and add them together. So, for example, well, let me be careful here. So, here's what's going to happen. First step is to recognize it's Cauchy Euler. Once you recognize that it's Cauchy Euler, recognize that it's linear. So the first step is determine the homogeneous solution. So in this case, we're going to have something that looks like at squared yh double prime plus bt yh prime plus cyh is 0. So we're going to replace that by 0. Then we're going to determine the particular solution. And for the particular solution, It's just like we had before. The only difference is that we're going to have our g of t on this side, and we're going to solve this basically without concern about the homogeneous part. And then when we're all done with this, we're going to sum yh and yp. So our solution is going to look like yh plus yp. And notice here, this is exactly the same as what we've done before. There's no difference here than what we did before for constant coefficient equations. The only thing that's going to be different is the ways that we solve for these two things. And when we do this, we're going to basically make the assumption we have already discussed. This part for the particular solution is going to be much more difficult than what we saw before. In particular, it's going to be very hard to make a guess for what we think is going to be there. So we usually don't even try. And what we're going to do is use something called variation of parameters. And variation of parameters is going to be just like reduction of order, except that I'm going to use both homogeneous solutions and use that to figure out our particular solutions. Okay. So let's just do a quick example. And for this example, suppose we have tx double prime minus 2x prime plus 2 over tx is 0. The very first thing you need to do is recognize that this is Cauchy-Euler. And one of the difficulties here is that this does not look like it's Cauchy-Euler because this is different than what we have in the book and the way it's normally presented. You need to recognize that if you multiply everything by t, so if you distribute that t, these cancel, then t times 0 is 0. This is now in Cauchy-Euler form. And now I can go through and do what I need to do to solve this. And the first step is to make an assumption about what the solution looks like. So we're just going to use something times t to the r. We're going to plug this into the equation, see what it implies about c and r. And again, this is very similar to what we did before with constant coefficient equations. The only thing that's different is this assumption, but the rest of the process is exactly the same. So the derivative of this is going to be r times ct r to the minus 1. So we're assuming r is a constant. And now when I take a second derivative, when I bring the r minus 1 down, and then reduce r minus 1 to r minus 2, these are the functions I'm going to plug back into my original equations. So t squared times x double prime is t squared times r minus 1 times ct to the r minus 2 minus 2t, then x prime is rct to the r minus 1 plus 2 times x, and x is ct to the r is 0. So I just plugged into this equation. Now I'm going to do the algebra. I'm going to leave r times r minus 1 times c alone. T squared times t to the r minus 2 is t to the r. I'm going to take the 2t c and leave alone, but r, sorry, I got in a hurry and screwed up. So I'm going to have minus 2rc, those are the constant terms. T times t to the r minus 1 is t to the r. And I'm going to leave this last term alone. Now I notice every term has a ct to the r. So I can factor that out. And I'm left with r times r minus 1 minus 2r plus 2. This is our solution, and we don't want c to be 0. Right, if c was 0, we don't have a solution, so that implies that this polynomial has to be equal to 0. And now I'm just going to see what this implies about r. So I multiply this r through, collect like terms, so I get r squared minus 3r plus 2 is 0. I see that I can factor this. It's r minus 2 times r minus 1 is 0. Is that correct? So plus 2 minus 2. Yep. So that means r is either 2 or 1. So my this solution, it's already homogeneous, is going to be c1 t squared plus c2 t to the 1. Do we believe that? So we can do a quick check to see if that's the case. So what was our original equation was tx double prime minus 2x prime plus 2 over tx is 0. We assumed x is in the form of xt to the r, and then found that r is 2 or 1. So that means that our solution then looks like c1 t squared plus c2t. And now if I want to check to see if this works, I can take the first derivative. So derivative of t squared is 2t. Derivative of ct2 is c2. Second derivative is going to be 2c1. Derivative of t is 1. Derivative of that's 0. Plug that into my equation. So t times x double prime is t times 2 times c1 minus 2 times the first derivative, which comes from this term, is 2c1t plus c2. And then plus 2 over tx, and then we said x, is c1t squared plus c2t. So let's expand everything out. What's wrong here? Yeah, that should be 2 over t. I wrote that down wrong. So this is 2t times 2c1. Multiplying this 2 through, I get 4c1t minus 2c2. Multiplying through by the 2 over t, I'm going to get 2c1t plus 2c2. So that t cancels and that t cancels. Let's see, notice here I've got a minus 2c2 plus 2c2, so those terms cancel. Here I've got a 2c1 minus 4c1t. That's minus 2c12 plus 2c1t. So those terms cancel, and I'm left with 0, so that's a solution to my differential equation.